Welcome to Radar System course. Today we see what will be the radiation pattern of a field array antenna and how this field array antenna that will be electronically steered here. That will see. So now we consider this antenna, field array antenna. So each and every element, that spacing between the element will be a D here, and we consider this array antenna is a broadside array antenna because radiation pattern is a broader side of this antenna. All the elements are placed linearly, so that's why it is called as a linear broadside array antenna, and the radiation pattern is perpendicular to the axis of this array antenna. Okay, so now the spacing, we say it is about a constant, that is a d here, and now we need to excite all the elements with the same amplitude, but there may be a variation in the phase. So what will be the difference in the phase between these two elements to be considered, so that we will get a radiation pattern towards a given particular direction. So for that purpose, so what will be the phase requirement for each and every element, and what will be the phase difference between this particular element, that we need to be discussed here. So for difference in the phase of the signals in adjacent element, that can be right, or we can write in the form of psi is equal to twice pi, then d by lambda, a sine of theta. So theta is nothing but what? In which direction your signal is propagating or transmitting. So in generally we consider that our antenna here, radiation pattern, it is perpendicular. So that's why we consider that is about a normal here for this. And we can consider that a signal, it will be incoming from the target. For this incoming signal, along with a normal, we say that this angle is about a theta with a normal. And this theta is nothing but the direction of the whatever the incoming signal from the target or radiation from the target. And then we see here the difference in the phase. Okay, difference in the phase of the signals in different in this but element here. Okay, that is nothing but Fi. Whatever the adjacent element we have, for this adjacent element, that psi is the difference of the phase here. And generally we consider that the amplitude applied to each and every element will be a constant, and the phase for the each element will be different. There are the types of a array antenna. So whether we apply the same amplitude, same phase to each and every element, or whether we have variation in the amplitude but same phase, or variation in the phase but same amplitude. Likewise, based on that, there are the types of a various array antenna there. In this case, we consider that a array element, each and every element, we are applying a constant amplitude. And for our convenience, we are supposed to consider that amplitude of this particular each and every element we are applying, it is to be a 1. So if we consider a total voltage applied, okay, whatever the amplitude we supposed to apply to each and every element, if we write the total voltage, in that case we say that EA is equal to sine of omega t plus sine of omega t plus psi plus sine of omega t plus twice psi plus up to dash dash plus sine of omega t plus n minus 1 because our element is nothing but 1, this one is a 2, this one is a 3, 4, 5, 6, then we can say that this one is about the nth element. That's why n minus 1 element, that is about the difference. So we will get that a total voltage or summation of the voltage here, that is nothing but what, EA is equal to sine of this particular term. And we can rewrite the term of EA here with respect to a sine of omega t plus n minus 1. Here, what will be the phase difference between the each and every element, and a sine of n psi by 2 by sine of psi by 2. Now, this particular component, we can say that sine of n psi by 2 and sine of psi by 2, it is called as a array factor here, and that will provide you. So, what will be the magnitude of the field intensity pattern or a radiation pattern of a signal? And this factor, if you consider, is with respect to what will be the phase and what will be the frequency here. And then this one is just talking about in terms of amplitude, and this one is about giving the relation with respect to a signal frequency and a phase here. So what will be the radiation intensity by this all the elements? That will be the summation of radiation of each and every element, and that will give you the radiation pattern in terms of the this particular term. So what will be the field intensity pattern? So field intensity pattern we can write with respect to what will be the angle here, that irradiation or incoming signal we are getting. So we can write here EA of theta is equal to sine of n pi d by lambda sine theta divided by sine of pi d by lambda into sine theta. Now in this case, this term, that is n psi by 2, that psi by 2 we have replaced with a twice pi d by lambda into sine of theta here. So we are replacing this term so that we are getting a radiation pattern, that E of theta is equal to sine of n pi d by lambda sine theta here. So EA of theta, that is about a radiation, that intensity, if this theta, if it will, this theta will be a 0, in that case the pattern has a null, or we can say that it has a 0, because this particular factor is 0, sine of theta. If the numerator is 0 or denominator is 0, this whole term will be 0. Or otherwise we can say that we are getting this particular pattern, it will be a 0 when we can say that n pi d by lambda sine of theta is equal to 0 plus or minus pi plus or minus a twice pi up to dash dash plus or minus n pi here. So this particular factor we say that it will be a 0. Okay, this particular term, if we consider this one is a 0, sine of 0, 0 here, this numerator term will be a 0. Or in another way, denominator term is a 0 when we have a pi d by lambda sine of theta will be a 0 plus or minus pi plus or minus twice pi plus or minus n pi. so that this particular term will be a 0 here. So both the term, either numerator or denominator, even if it is a 0, so means your pattern have the 0 here, so means your field intensity will be a 0 there. So when we are getting the maximum radiation intensity at what particular value of this n pi d by lambda or sin theta, so we need to find out where we are getting the maximum radiation intensity. So we can find E of theta, we are getting the maximum when a sine of theta, this becomes what? A plus or minus n lambda by d here. So we can say that a sine of theta is equal to plus or minus n lambda by d. At this particular instant, we are getting the amplitude of the radiation intensity. It will be a maximum here. Otherwise, what happens if sine of theta is not is equal to plus or minus n lambda by d? So in that case, we can generally consider that a radiation pattern of an antenna is likewise. Okay. So for this particular broadside array antenna, it is a perpendicular to the axis. So we just draw a radiation pattern of this antenna. It is likewise. So this one is about a radiation pattern of an antenna. So we are getting the maximum intensity when we have a sine theta is equal to plus or minus n lambda by d. So here we are getting the maximum intensity. Otherwise, what we are having, if the term sine of theta is not equal to in the particular term, so in that case, other pattern we are getting means radiation intensity can be with a side lobes, or we can say that a back lobes, but only at this particular sine of theta n lambda by d we are getting the a maximum intensity. Other than that, we are getting the maxima at this a side lobes, that is called as the grating lobes. And these side lobes or back lobes, these are undesirable to the antenna. So we need to design a antenna in such a way that we are getting a maximum radiation only in a one direction. If our antenna is providing, or if our antenna is not directed in a given direction, so we are getting the grating, or we are getting the side lobes or a back lobes, and because of this side lobes and back lobe, so our radiation intensity or irradiation signal, radiating signal will be diverted to the all the directions. Means we are getting the maximum radiation intensity at this particular point, and other maximum radiation intensity we are getting at this particular side lobes or a back lobe. So we say that it is about a 0, it's first null. Okay, so we can say that at this particular point, radiation intensity will be 0 at this particular location. This one is about a first null visit. So similarly, we have a first null, second null. So instead of polar pattern, okay, if you draw a amplitude pattern of a antenna, so in that case, this one is the maximum radiation intensity. And along with that, we have the a side lobes. So here we can say that at this particular point, this one is a first null occurs. Here we can say that a second null occurs. And here we are getting the a maximum intensity at this particular point. So maximum radiation intensity we are getting at this particular region when we can say that sine of theta is equal to n lambda by d. So from this we can find out this value of a theta. Okay, so we can say that a target direction. This theta is nothing but what? A direction of what? Signal or radiation incoming signal from the target there, or echo we are receiving. from the target. So from this we can find out this radiation intensity, and generally we can consider that a grating lobes, or we can say that side lobes or a back lobes, they occur at a different directions. So mostly we can consider that for a given particular antenna, we say that a broadside one. So we are getting the radiation pattern at the back side of it. So means we can say that it will be what radiation pattern opposite to it, or we can say that this one is nothing but a side lobe shape. So now from this we can find out other than this maxima, these maximas occur. Okay, this one is the main radiation pattern. Okay, main radiation pattern of an antenna. These are again a side lobes. Here we are getting the maxima. So maxima occur at a main radiation pattern. Maxima occur from the side lobes. Maxima occur at a back lobes. But this maxima occurs at these back lobes. These are the undesirable signals. So from in another way we can consider this signal is of no use for a radiation. Okay, because area coverage by the antenna depending upon the main lobe. This one is nothing but a distortion or a noise that came because elements whichever we are using, they are not identical. So generally we consider that a isotropic element is to be used. That is about a theoretical term. But in a practically isotropic antenna is not possible. So we consider that a isotropic element is nothing but a similar component or a similar element in the array antenna. So why this word phased array? Because we apply the variation in the phase to the antenna. Okay, for each and every element we apply the different or some particular values to different phase to each and every element. But the difference in the phase is nothing but twice pi d by lambda into sine of theta, and that theta will provide you the direction of the incoming signal. So at this particular moment, we say that a theta is likewise in that direction. Suppose in another way, we can say that a theta here. So means our target is echo signal coming from the target from this direction. If I say that theta like this. So in a different directions, we are getting the signal. Okay, other. So here we are varying this phase of each and every element so that phi will be changed. Okay, phi will be changed. So phi will change. If phi changes, so theta changes. Okay, based on the variation in the theta incoming signal, phi changes. So total difference applied to the particular whatever the antenna element, each element there, that will provide you the direction of a target, in which direction the target is present. So means we need to focus in a given particular direction based on the whatever the a phase here, and then we can consider that direction of the given particular phase, that will be useful for understanding the what will be the position of the a target here. So instead of varying whole assembly antenna assembly there, or whole whatever the dimension of that antenna, everything through the motor, instead of that, if we vary the phase to each and every element, so that our beam directions will be changes here. Now this will give you the a complete this particular value will give us the a radiation pattern intensity there. Now if you normalize this, okay, if you normalize this EA of theta by n here. So because we have the n number of elements, that's why we can consider that a n here normalized. So in that case, radiation pattern that will be normalized to the given particular amplitude. So this one divided by n, so we'll get the a normalized pattern there. So we can write here what will be the normalized radiation pattern value. So this normalized radiation pattern value, we can consider here a GA of theta is equal to whatever the amplitude we have divided by n square is equal to sine square n pi d by lambda sine of theta divided by n square sine square pi d by lambda sine of theta. Now this one is the irradiation pattern of the signal, and here we consider that a spacing between the element, that is the d here. So at what value of the spacing between the element we will get the maximum radiation here. So for that purpose, so what we need to consider here, what will be the radiation pattern of an antenna, and from this radiation pattern, so what will be the half power beamwidth. So half power beamwidth means what? If we consider that this one is the radiation pattern of an antenna. Okay, this one is about the radiation pattern of an antenna. Here we can get the maximum intensity. This one is about a maximum value of a radiation here at this particular point. So from this maximum radiation point, if we find out a 3 dB point here, okay, these are nothing but a 3 dB point. So from this particular 3 dB point, if you draw a line, okay, so we will get this beam width. This beam width is called as a 3 dB beam width. But instead of a decibel, if we consider only the amplitude or a voltage, and we just consider that half of it, so in that case we are getting the half power beam width. This one is a 3 dB beam width. Here we are writing in terms of a dB. If we are writing in terms of amplitude or voltage, we can say that it is nothing but a half power beam width. So 0.5 of a maximum value. So we locate the 0.5 of a maximum identical point, and then we will get the beam width, and this is called as a beam width, not a bandwidth. Okay, so we can write here this one is called as a 3 dB beam width. Okay, so now what will be the maximum beam width, in which direction we are getting the maximum beam width? So generally we can consider that a factor of a beam width, and that will be based on the this particular a component here. So generally we can write that beam width, if the spacing between the antenna element is a lambda by 2, you can say that a d is equal to lambda by 2, and then from this we can find out the beam width theta b for the antenna is equal to 102 by n here. And then this one is the value we are getting for the particular spacing of the element. If the spacing of the element is varying, okay, instead of a lambda by 2, some particular number in terms of a wavelength, so then a beam width will change it. So at what particular value of spacing, what will be the beam width value, that we need to be find out. So this beam width, again, it is depending upon that how many number of elements we are using. this radiation pattern, their intensity is again depending upon that how many number of elements we are using. Based on that, we will get the beam width as well as this radiation pattern. Okay. So we consider that radiation element in a given particular direction, broadside array here, and we supposed to not require any back lobe there. So what particular condition is to be used here so that will not get any back lobe or a side lobe there. So for that purpose, we need to know about a element present here in this array antenna. All elements are a directive, only in one direction. Okay, so directive element we supposed to be considered. Then for this particular directive element, so we are getting the radiation pattern that a g of theta. It consists of a element factor as well as the array factor. So in that case, we can write here a g of theta. Okay, we can write here a g of theta is equal to what? This ge of theta is nothing but a element factor, and sine square n phi d by lambda sine of theta divided by, here we have n square sine square phi d by lambda sine of theta. So this one is nothing but what? We have a ge of theta and a ga of theta. This ge of theta is nothing but the element factor, and this is nothing but a array factor. And that array factor, it is in terms of a individual element of a radiation here. So means every element having some particular radiation. So if we consider, because all the elements are identical we are using, so every element have some particular radiation. That's why it is about a G for the single element here. Okay, this one is about radiation. We consider that a G for the single element. And this one is nothing but the array factor. So how many number of elements we have? Based on that, array factor will change. So this factor will be changes here. And this element factor is a constant now. Okay. So that we are getting a radiation pattern of an antenna. It consists of a element factor as well as the, we can consider that a array factor. So every element having some particular radiation here. So that's why radiation from the array is generally it is called a space factor and element factor. So element factor into a space factor, so we'll get the total radiation of the antenna there. So if the element spacing is not equal to a lambda by 2, generally we say that element spacing is to be a lambda by 2. If it is not in terms of a lambda by 2, then a grating occurs. Grating lobes occur. Grating lobes is what? We have a side lobe, we can say that back lobe. Okay. So if that spacing, that d is equal to what? A times of lambda, then a grating lobe occurs at theta is equal to plus or minus 30 degree, and we can say that a 90 degree plus or minus 90. Okay, if d is equal to twice of lambda. So if the d is equal to lambda by 2, there is no grating. Okay, means no side lobe. So we need to consider that every element, they have some particular beam width. Okay, they have some particular beam width, and then from this particular beam width, every element we say that beam width, just like a radiation pattern here, and it has a beam width. This one is nothing but the beam. Okay, they are nothing but the point. So what will be the beam width for each and every element? So that a total radiation pattern of an antenna, total element. So every all elements will consider here to obtain the what will be the beam width. So if we consider the beam width, if it will be less than the 60 degree, okay, that whatever the element we consider, if their beam width will be less than the 60 degree, okay, so in that case, the grating lobe can be removed here. Okay, how to remove or suppress that grating lobe? So we can use every element, and that every element their beam width is to be a below 60 degree. Okay, then a grating lobes can be a suppressed here. So from this we can consider a radiation pattern in terms of element and a array factor. Now here we consider that a one dimensional array, we can say that all the arrays in a single dimension. But if we consider that a two-dimensional array pattern, okay, if it will be a two-dimensional in a case, so in that case, a g of theta, instead of that we can write a g of theta a and a theta a, okay, instead of g of theta, theta a and theta a is equal to what? So g1 of theta e into g2 of theta a. So what do you mean by theta e? Theta e is nothing but what? It is nothing but a angles, okay, towards the elevation, okay, whatever the elements we supposed to consider in terms of instead of a single dimension, it will be in a two-dimensional there. So likewise, we can consider that the arrays are placed in the different directions like that. Okay, so we consider that this is nothing but the array pattern now. Okay, so we can consider that array pattern here, or we can consider instead of a linear here. So this one is about a linear case. But if we consider in a different dimension, okay, similarly we can, earlier we say that it is about a square shape of a different path. How we are placing the element? This is nothing but the patch array antenna. Okay, in a two-dimensional. So normalized radiation pattern that we are getting from the theta e, the elements those who are present in the elevation that belongs to the elevation, and this theta a, those elements are belongs to the azimuth. So antenna elements placed in the, so antenna element placed in such a way that we are getting the angle of elevation, or we can say that is azimuthal. So that how many number of elements are present in a theta e or in a theta a, based on that we are getting this irradiation pattern there. So in that case, how many number of elements that consist of a theta e and number of elements that will consist of a theta a. So this will gives us the radiation pattern of the antenna there in a two-dimensional case, not in a single dimension. So for that purpose, we consider that elements in the azimuth as well as the elevation. And now our aim is here to understand that electronically steered phase antenna. So this one electronically steered phase array antenna. Okay, array means what? A group of elements we consider. Okay, group of same element, same antenna element we consider. They formed or they placed in a line, so linear array, and they form a antenna that called as a array antenna there. Okay, so identical element we use here. And then a steering one, beam steering. Okay, beam steering means what? We consider that a array, okay, beam steering means what? A antenna radiation pattern will be focused in a given particular direction. So how it occurs there? How it possible? How it is possible? So when we consider exciting the element with a varying a phase, okay, means every element we consider that if we vary the phase, so that incoming signal direction will be changes. Means in another case, we say that, for example, we have the broadside array radiation pattern will be likewise. If the phase of that array changes, so it will be likewise. If the phase is further changes, it will be likewise. If the phase is further changes, it will be likewise. Okay. Even in a reverse also. Okay. Even in a reverse also. So how we can consider? So instead of this one here, so this one will be radiation pattern. This one will be radiation pattern here. So likewise. So if we change the phase here, so beam of an antenna will be changes. And that is nothing but what? Applying the phases to each and every element. So beam position will be changes. So direction of the beam is here likewise. Here likewise. Again it will be changes. So direction of the beam is changes. That is called as a steering. So how we are changing the direction? By applying the phase to the every element. So in this case, every element we are applying a same amplitude but varying the phase here. Whatever the signals we are applying, it has the same amplitude but the phase is varying. And we need to consider that spacing between the element is to be equal here. So generally we can say that D is the equal spacing here. So if we consider that the variation in the phase to each and every element and we have the equal amplitude, then a beam direction will be changed. So instead of using the mechanical assembly to change the direction of the beam pattern, so we can use a electronically steered phase array antenna so that we can change the direction of the radiation pattern. So if we consider that whatever the phase difference between the element, okay, we say that a spacing between the element is D and every single element we are applying the signal has the equal amplitude. So every element has the same amplitude we are applying. If we consider that if the same phase is applied to all the elements, okay, same phase is applied to all the elements, then the relative phase difference between the adjacent element is a 0. Then the position of whatever the radiation pattern we are getting from this antenna, so it will be a broadside, means we can say that it will be a perpendicular. In that case, theta will be a 0. So this one is about the case here. Okay, so this one is about the case here. So in that case, theta is equal to 0. So if we are applying the same phase to all the elements, so that relative phase difference between this element will be a 0. So then theta will be a 0. So this one is about a radiation pattern. So radiation pattern will be a broader side of an antenna. So then what is necessary here? Is theta is 0 here. What is necessary for a steering? So if we varying the phase applying to the each and every element, then your direction of the beam will be changing. So we need to consider that what will be the phase we are applying to each and every beam. So in that case, the phase, or we can say that a direction of the main beam is at an angle, whatever the theta we consider. So in that case, we are getting the phase difference is equal to what? A twice pi d by lambda sine of a theta. So in this one is about a theta direction. And then we can consider that a phase at each and every element is nothing but what? Phi c plus m phi. Okay. And this will give you, so how many number of elements we have? M is equal to n 1, 2, 3, 4, 5. Okay, likewise. And this phi c is nothing but a constant phase applied to all the elements. So that a phase at each element we are calculating constant plus m phi. So phi is nothing but through this. So, so radiation pattern, where we are getting the maximum, if theta is equal to what? Is equal to theta 0. So in that case, sine of theta will be of a sine of theta 0. So we are getting the a maximum radiation, means it will be a perpendicular generally, if we consider that is about the same phase here. So in that case, we can calculate a radiation pattern, or we can obtain the radiation pattern g of theta here in terms of theta 0 and this particular theta here. Now position of this particular radiation pattern other than this perpendicular we consider likewise this one. So we can change that varying the phase there. So how to vary the phase here? So we need to apply a phase shifter. Okay, we need to apply a variable phase shifters to each and every element at a feeding point, so that a steering of antenna beam with a variable phase shifter will be possible. How it is possible? So for each and every element, if we apply here at a feeding point, so we say that phase is to be a variable, that is about a phase shifter we are supposed to consider. Okay, so this one is a twice pi, likewise. So, and this one is a variable. Okay, everything will be a variable. So that a steering of a beam steering will be possible if we change the phase there. And then a beam width again changes if we change the steering. So then a beam width will be changes. So generally we can consider that scanning increases if your radiation pattern will be perpendicular to this antenna. Okay, so broad side of this pattern. So this way here. So this way. So scanning will be. In that case, if the beam is likewise, if our beam will be perpendicular, so then scanning will be a maximum. If the beam will be likewise, okay, so then beam will be area coverage. Okay, it will be changing. So we need to consider that. So at what particular scanning angle? So what will be the beam width here? How that beam width is changes here? At what particular value of a theta we are getting the maximum beam width? So that we can consider this varying the phase shifter with the given particular value, and we can change the beam width with a steering angle. Okay, change the beam width with a steering angle. So this one is about steering electronically steered phase array antenna, and we can vary the direction of a radiation pattern Electronically means varying the phase of each and every element, and we'll get the radiation pattern. And we have seen that a antenna radiation pattern, radiation intensity is depending upon that every element, whatever the radiation pattern occurs obtained from the every element. And how many number of elements we are using, so according to that, the radiation intensity will be changing. So with this, we stop here. So thank you all.